Hi guys, welcome back to the Astro Imaging channel. Tonight's session, plate solving in the PinPoint astronomic engine, going to be presented by Bob Denny. Bob Denny is the developer of PinPoint and is probably the best person to have on to discuss it. But as always, before we go into that, I am going to show off our image of the week. Excuse the infinite screen right there for 1 second. There we go. Our image of the week is M8, M20, NGC 6559, and IC 1275 by Christopher Scott, with the Lagoon and the Trifid Nebula, and I'm not quite sure of the names of the objects, if they have proper names in the top left. But first of all, thank you, Christopher Scott, for submitting. And as always, you guys can submit your images on our website and possibly be shown off here. Thanks again, Christopher. As I jump back over, let me get rid of that for you. I don't know if that drives you guys as crazy as it drives me, but all right. So Bob Denny is here, and Bob, the camera is yours.
Okay, good evening. As he said, I'm Bob Denny. I'm the author of PinPoint and also ACP Expert, but we won't be talking about ACP Expert tonight. I'd like to try and keep this on topic, talking about plate solving in general, really. I'll say a few things about PinPoint, just what makes it different from the other ones, but I'll also say things about what makes the other things different from each other. So I'm going to try very hard not to make this a sales pitch. One other ground rule I'd like to establish is I would prefer greatly not to accept tech support questions like I can't solve this image. Why not? And I will talk about the reasons you might not be able to solve the image, but that is totally insufficient data for me to be able to help you. If you're a PinPoint customer, you can get on our board, you can post a log file, I can see what you're doing, I'll take an image, but generally samples of one, and this is point number one I wanted to make, samples of one are a very bad way to judge plate solving engines anyway. They all make errors, all of them, once in a while. And the trick is for them to work right most of the time. You know, if you don't have any stars in your image, or too few stars, or the stars are really weak, or they're misshapen, or if you're shooting at an area of the sky where there aren't stars in the star catalog, and I'll get into that in a minute, or you don't have your plate scale anywhere near correct, all of those can be reasons that it won't solve. And if the engine's not an all sky solver, that is, if it doesn't know how to solve no matter where you think it's pointed, and that's a much more difficult thing and much more time consuming, then it won't solve because it's not ever going to try enough combinations of stars to get them to match. So I couldn't possibly solve your tech support question tonight, period. So let's just start. What does plate solving accomplish? Most people encounter plate solving. I want to get back to this. I'm going to write this down as a note. User settings. That's one of the things that distinguishes the different plate solving engines. Some require no settings and some require a lot of settings. And that's a big difference. And what one of my goals has been is to make PinPoint, at least, not settings dependent. You just put in an approximate plate scale and an approximate position and it should solve, period. Rotation free, it shouldn't matter. Distortion free, we'll get into all that. But anyway, I want to answer that question as soon as it came up here. So getting back to what I was going to say, most people's encounter with, how long do we have? An hour, half hour? I forgot to ask.
We have an hour.
Nominally.
We could go under.
All right. Okay. I just want to keep my eye on
the end, so we'll see.
I want to keep my eye on the clock so I don't, drag this out or overrun it. All right. Let me try again here. Most people's encounter with plate solving is when their telescope doesn't point well enough. And you're trying to figure out where your scope's pointed. It's either a really inexpensive scope that if you touch it, now it's out of whack and has to be resynced, all the way up to a scope that's got problems with the gears and all the different reasons that a scope doesn't point well enough. In that case, the plate solver's end task is to simply look at a field of stars and then figure out where it's really pointed. Really. So what a typical automation program like Sequence or CCD Commander or CCD Autopilot or ACP Expert, all of those do pretty much the same thing, and with details differing, but they'll send the telescope. You'll tell the telescope where you want it pointed, and by that I mean your RA and DEC. The scope will go there, but it won't really be there. It'll be somewhere else. And so how far off is it? Well, you take a picture and then you send it to a plate solving engine. The plate solving engine goes, oh, you're really pointed here. So then you go back to the scope and you give it the coordinates of where it really is and sync it. Or in the case of telescopes such as the Paramount with the pointing model, you don't want to sync into the pointing model. So instead, you would tell the telescope, no, you're not pointed here, you're pointed here. So it would just move the scope so that your target is in the center, even though the scope's telling you it's not really pointed at the target. It is. So either way, the idea of the plate solver is to give you the coordinates at which your telescope is really pointed. So if there's anybody here who doesn't get that, just type something into the message box and I'll explain it a little bit better. But without understanding that, we're not going to get very far. Okay. Somebody just jumped in, but that wasn't a message. So that's the fundamental purpose of a plate solver. But there's so much more that it can do depending on what it's designed for. Some people use it to measure the positions of stars in the field. So it can also act as an astrometry engine. And by that, I mean it can detect each of the stars or whatever in the image and then get very precise XY coordinates, convert that to an RAN deck so that you can go through the image and you can get an RAN deck for each star in the whole image. And that's a big deal. For example, and I'll show you in just a sec what happened with that. A year and a half ago last year, for the 2017 solar eclipse, a guy named Don Bruns went out and took images, and he wanted to repeat the Einstein light bending experiment, gravitational light bending experiment. And for that, he needed extremely accurate positions for the stars. And then he could see if they actually moved with respect to where they would be or were before the starlight grazed the sun. So he went out and took the data, and then he came back and analyzed the data, which took 6 months. And that resulted in, let me bring this up, and I'm going to put my glasses on now because I just need, so it resulted in him sending me a message, which I'll show you first, which was a big thrill for me right here. Hi, I've completed the report on my 2017 solar total eclipse experiment to measure the gravitational deflection according to Einstein's general theory of relativity. It was a challenging project, but everything went well in Casper last August. My accuracy far exceeds any other eclipse test, missing the theoretical value by less than 0.05%. That just made my day because he used PinPoint as a plate solving engine, but also to measure the locations. Oh, I better get this off of here. Just a sec. How do I get this back? Now I'm not getting the pop out. Oh, I didn't share the screen. Duh. There we go. Let me put this back again. I didn't get that up. Sorry. So here's the message he sent me. Don't pay attention to all this other email junk here. And as you can see, I got this on the 1st of February. It was quite a thrill to see. And as a result, Don's paper got published in several places, but most importantly, here. I'll give you this screen. That's not right. Let's try this again. Here we go. Sorry, I'm just a little bit slow on this. And one more for good measure. This is a nice article. Here's a picture of Don. And it was published in Classical and Quantum Gravity. And then one more place where final paper. Here we go. Nope, that's not it. That's the... I have one more to look at here. Just a sec. I know it's in here. IOP. Well, this is what I thought it was. Centroiding paper. That's not it. Oops. Well, anyway. Oh, archive. Here we go. So it was published here also. And you can download this paper from archive. I think I can probably provide these folks with the links to this stuff, right? Is there a way?
You can put it in chat.
Oh, all right. Well, here's the archive one. Boom. Ready, and then the Classical and Quantum Gravity article is here. And last one is the IOP article, which is here. Okay, here's the key to this. Besides just calculating, well, let me get rid of this screen thing. Okay, besides just calculating, you have a field of stars, right? And you calculate the positions, and then I'll get into this in a minute. You somehow convert those into RAs and DECs. But what you start with is a set of XY measurements of each of the positions of the stars in the image. They can be, that's an art in itself, is centroiding. And depending on how it's done, they can have little systematic errors, and they work better or not so well in different varying signal noise ratios. And that's part of it. But the other part is when you convert from X and Y to RA and DEC, every optical instrument has optical distortion. So depending on where in the field the star is, it may get deflected a little bit. There's pincushion distortion, sin X over X distortion, skew distortion. All optical systems have distortion like that. So somehow you have to remove that. And the way PinPoint does that, well, I won't get into PinPoint. I'd say the better plate solvers have a way of looking at that, and as they are matching the X and Y to the RA and DEC, they're starting to see a pattern of that optical distortion and construct a model of it automatically, and then they reverse that optical distortion out. Dr. Bruns has used PinPoint, the automatic distortion correction, to do that mapping, and as a result, his positions were hyper accurate. There were some additional things that he did, and they're in the paper, and you can see them, but fundamentally, removing that optical distortion is another thing that a plate solver might do. So what I'm trying to get to you is give you the idea of is that there's a lot more that meets the eye when you first encounter, or when you just use a plate solver to give you the coordinates so you can get your telescope pointed. And that's really the point I'm trying to make. So the process of plate solving, let me stop now and see if I'll put another 10-second blank in here for questions. And if you want to ask a question, just type wait and hit return, and then enter your question after that. So I know you're in the middle of typing. I can't see if you're typing. Okay. So if I see one come up, I'll stop. So the process of plate solving is as follows. The first thing you do is you bring an image in and you detect the stars in the image. You have to, there are a bunch of different ways to do that. There is an aperture photometry way where you use an inner aperture and an annulus with a gap between them. That's a typical method that photometry detecting software uses. And the annulus is used to get the local mean background noise in that area, and then you look in the aperture and you actually move this whole thing across the image in a way that allows you to detect and center on each one of these things. So there's the aperture photometry method, and then there's it's called a box moment method that's was developed by a guy at Lunar and Planetary Laboratories in Tucson named Ken Mile. The box moment method, that's another one. Another one is point spread function fitting. So you'll go detect real, bright pixels, and then you try to fit it with a point spread function. And if it doesn't fit, it's not a star. So you have those choices. Each of them has their strengths and weaknesses. And you have a choice. Typically, in some plate solvers, you actually have a choice of which one of those centroiding methods and detection. So detection and centroiding is typically done at the same time. You're looking for star shapes or bright pixels against a what background. The background may have shading in it. So if you try to take a flat estimate of the mean background across an image, you're not going to make it, because the stars over here, or the weak stars over here, won't get detected, and you'll have a bunch of noise over here. So a lot of times they'll either try to flatten the background, or they'll divide the background up into tiles, or in the case of the aperture photometry, it uses the annulus around the center to measure a very local background mean. So as I say, they all have their strengths and weaknesses. We don't have time to get into all the blood and guts of how all this works. So that's step one. Now you'll have a list of stars and their XY coordinates in the image. That's a starting point. The next thing you have to do is go out and get a list of stars that are known to be in the area where you think this image was taken. Now, this would be for non-all sky. For all sky, it's more complex, and I will get into that in a minute. But just so you can understand how it works in the most straight, the simplest way, the next thing that happens is you have an image that's supposed to be pointed at some place in the sky, so it will go out and pull stars in from USNO A4, A2.0, or UCAC4, or any one of the guide star catalog, whatever. It'll pull the stars in from the catalog and may do a proper motion correction on the stars as well. And now you have another list of stars in the area. Oh, and it usually will pull them in from an expanded area. So if you say your telescope's pointed, or your image was taken here, and it's this big, it'll pull stars in from around the area so that at least it can find stars if there is a pointing error. But there's a limit to that, because the more stars you pull in, the more combinations you have to look at, the more things you have to test against, and the slower it solves. So that's quite an interesting trade-off. Anyway, you pull in the stars, you now have XY from the image, and you have RANDEC from the catalog. So then you have some number of image stars and some number of catalog stars. The next thing you try to do is to get them to match. And it can be rotation and scaling. So the one set could be bigger, scaled up, wider, or what I'm saying, image scale, zoomed in, zoomed out, and also rotation. So you have both rotation and scaling that you have to work on. Typically what happens, I can tell you how it's done internally with PinPoint. Others use similar techniques. PinPoint develops a list of all of the combinations of all the stars in both the catalog and in the image in as triangles. So you have a huge list of triangles, and what it does is it looks at the ratios of the lengths of those triangles, and that set of triangle leg length ratios is what is matched from one to the other. So eventually it will find a couple that look like they're about the same. They could be scaled completely different, but the leg length ratios will be the same regardless of the scaling and regardless of the rotation. So the next thing it tries to do is, if it's got a possible match, is it will now develop a transform for that and match the stars XY against the Aryan deck. It'll take the transform and it'll transform the stars into Aryan deck, and then look at the errors between where it thinks the star is and which one it thinks it matched. And it'll develop a whole list of those things and then give you a general idea, is this a good match or not? And that's a test. If it looks crummy, it'll go back and try some more triangles, and they'll go round and around and around and around like that until typically it will find one that, bam, okay, this looks like a real thing. The next thing it will do is it will refine the transform by, again, an iterative fitting process. And it's at this point that the better plate solvers will now start to plug in the optical distortion. I need to stop at this point too and explain that there are different projections. An image taken against the sky is being taken against a spherical surface, right? So you think about it. The sky is a sphere, and yet it's projected onto a flat surface. So when you project a spherical image onto a flat surface, the projection is most commonly called a tangent plane projection. And in the FITS world coordinate systems, that projection, the ideal projection for that instrument, is in there with it. And virtually all amateur scopes use the tangent plane projection. So you have that projection is already a form of optical distortion, but it's a pure transformation, two-dimensional transformation that's just the way it is. So when this fitting process occurs, you're telling it this instrument should have a tangent plane projection, but it's going to have some distortion across the image. That fitting process, again, will start to generate an estimate of the optical distortion. And what it's shooting for is a perfect tangent plane fit. So it's transforming the stars, the XY, by tangent plane before it ever tries to compare with the RAN deck. And then it sees additional residual errors and it will say, this is optical distortion. So it's, it grinds away on that. And it might do this, go round and round and round 50 times. And each time it does it, the error will get less and less and less and less. And boom, finally it'll say, okay, this is so good, there's just pointless for me to keep trying to make it better. At this point, the plate solver has calculated the optical distortion. Here's the advantage of that when you're doing just general plate solving, is if it's fast enough, you'll get more stars to match because you've got a closer fit all over the whole image. When I first started with this, I started with an unnamed telescope that had such hellacious sin X over X distortion that I could only match in 2 concentric rings. Everything else in the image wouldn't match. So I'd look at my match and I'd go, wow, amazing. So that's what, it was a guy named Bill Young, and he had 4 telescopes. He was the first guy to ever be designated as a survey by the Minor Planet Center. And he was just hammering away all night with 4 scopes looking for asteroids. And that he needed a fast automated system. That's sort of spurred me on to doing the optical distortion. And by the way, that predates the other plate solver's optical distortion by about 6 years. This was done in 2002, and the other stuff came in about 2007 or so. So that's the next step. Now you've got the solution, and from that you have the center point RA and deck, but you also have very accurate RAs and decks of all of the other sources in the image. So, and I'm just going to look and respond here. Yes, PinPoint certainly can be used without an internet connection. By the way, it's let me just go through the different solvers. That's probably a better way to do this. I don't want this to sound like an advertisement. Let me put this away. What do I have here? Okay, one more Don Bruns. I'll leave that up. Just 2 seconds here. I want to... Okay, so the plate solvers that I'm familiar with, pretty familiar with, are Astrotortilla, the PlaneWave Plate Solve 3, Astrometry.net, the network version, and ANSVR, Andy Galasso's local build for Windows of Astrometry.net. And God bless Andy Galasso. That was a beautiful piece of work, including his catalog downloader, because that was what was really made doing the Astrometry.net locally a pain. I mean, you still have to have the multiple mini gigabytes of data, but at least his catalog downloader is just a brilliant piece of work, and my hat's off to Andy for the whole package. Very nicely done. So you can run Astrometry.net, which is an all-sky solver, locally. So and PinPoint. I don't want to miss that. They fall into 2 general classifications. There are the all-sky ones and the not all-sky ones. Well, as it turns out, right now, can somebody answer to me, is Astrotortilla all-sky? It's not, right? I don't know that. If somebody can just say yes or no, is Astrotortilla an all-sky solver?
You know, I don't know. I haven't used it in a long time.
Okay, so if somebody wants to type the answer to that, it'd be great. All of the other ones, including PinPoint, are. And the way PinPoint does it is a very, well, let me go back and start with that Astrometry.net itself. That's a brilliant piece of work. If you give an image to Astrometry.net, no matter, I mean, it'll solve damn near anything. Some of them are really hard. It might work on it for 5 minutes, 3 minutes, 2 minutes, or more. The timeout on it's 10 minutes, and I have seen it take 7 or 8 minutes on some images. So, but it's trying to figure out where it's pointing anywhere in the sky, which is a huge job. You can only imagine the number of combinations. And by the way, they do it with quads instead of triangles. And looking back, it's probably what I should have done as well. But that's, you know, I just did it with 3 stars at a time instead of 4. So you have that you can use through the internet. They have a big beefy server up in Canada somewhere that you can submit images to. It's pretty busy. Sometimes it can get kind of slow. Then there's Andy Galasso's all-sky Astrometry.net that you can put on your own system. The downside of that is that you have to download lots and lots of data, but data is so cheap now, it really doesn't matter. So I would say if you have telescope pointing problems, having Andy Galasso's ANSVR and server locally is just a given. You should just do it. Now, how easy it is to integrate that with your automation software is a different issue. And some of them do it one way, some do the other. And then PlateSolve 3 from PlaneWave is also all sky. It's modestly fast, and it's just a command line program that you send off with an image, and it comes back to you with the fundamentals, the plate scale, rotation, and RA and deck. which is what you need to point a telescope, right? So what PinPoint does is it is a very lightweight plate solver. It's a little DLL that gets embedded into other programs. It gets loaded right into the program's address space. And as long as you don't need the all sky service, it's super fast and super lightweight. And it uses standard star catalogs in their exactly as shipped standard format without any reformatting or republishing or anything like that. If you need all sky service, there's a one-line call, one of PinPoint's many functions, and I'll show you a little bit about that in a minute. Sorry, I think I probably just yelled into the mic. It's a one-line, one-function call, and it does the whole thing. It actually uses PinPoint's object detector to detect the stars, and this is something I worked out with astrometry.net. Instead of sending the whole image across the internet, it just sends a little tiny star list, gives that to astrometry.net, and then boom, back comes the solution. And then PinPoint, now that it has a starting place, does a full PinPoint solution with all the optical distortion correction and the high resolution, high accuracy, and everything. So it's the best of both worlds, and that's how that works. And it's very simple to do. Somebody's mic is rattling around on their shirt.
Steven, I can't mute you for some reason. Would you mind muting yourself?
Okay, sorry. I didn't mean to interrupt things, but it was, I'm sure everybody was probably, it sounds better now. So that's the all sky. I can't and won't, because of our time, get into how all that works. If you want to see it, Andy Galasso's thing comes with a log viewer that you can use. In fact, let's have some fun. I'm doing well on time here. So I think, all sky means you do not have to tell it about where it's pointed. Astroturtia and PinPoint by itself, without going all sky, you need to give it a general idea of where you're pointing so that it can look stars up in that area for matching. If it had to look all the stars up in the whole sky and try and match it against that, the number of combinations of stars in the image and possible stars in the sky is astronomical, and it wouldn't be able to do it. So there's some other strategies that they use to do that, and they involve giant tables and being able to traverse them with special computer algorithms to do that. So to cut down the time. Anyway, that's what all sky is. All sky means the software doesn't need to have a journal. That's right. Larry's got it right. Okay, let's have some fun.
So, Bob, I have a question.
Yes, sir.
What if you have too many stars in the image? What do you do then?
Well, I can only speak for myself. Too many stars, I know astrometry.net prunes them. It takes the weak ones and just ignores them. And the same with ACP. It only uses the brightest 300 of each, and from the catalog and from the image. And so you could have 1 million stars in there, but it'll only take the brightest 300 of them and then work with them. So it doesn't slow things down. It actually will slow the detector, the thing that is looking for the stars down, of course, because it doesn't know how many are there. But there's ways, and I'm not going to give away my secret sauce, there's ways of making that run fast. And it's one of the reasons that I do the star detection before sending an image in PinPoint. PinPoint does the star detection and then builds a small list and sends that to astrometry.net or ANSVR instead of sending the whole image. The other reason for that is you don't have the bandwidth. If you don't have, and you don't need to be on the net, or you don't have, if you have low bandwidth, you're not sending a huge image. You're only sending a tiny list of stars. So both of those. Let's do this. I'm going to share my screen and I'm going to bring up Visual PinPoint. Let's see. That's this tool here. Can everybody see that?
Yes.
So this is just a little lightweight program that comes with the PinPoint engine. Right now, what's happened when I started Visual PinPoint is I loaded the PinPoint engine into this little program. And so all the settings that are here are specific to this program. They don't affect any other program that uses PinPoint. PinPoint knows nothing about any settings at all. Most of these settings, especially these solver parameters, never need to be touched. In fact, I can't say that anybody's had to mess with these for years. I've really gone all out to make it settings free. So right now I have it set up here for all sky to go to ANSVR. And what I'm going to do is start, I think I have a folder in here for that. Negative. Okay, I'm going to start ANSVR now from here. Astrometry.net local solver. Start it. Yes. Then I'm going to go bring up the the log viewer for that. Local server log. Watch the log, which is here. Okay. So we can look and see. There it is. It's just sitting there. So first, without using all sky, I'm using the UCAC4 catalog, and there are a bunch of images in here that we can use for tests. Some of these images will not solve, and that's on purpose. These are our test images. I'm not going to, let's see, why don't we solve them locally? Let me just give you an idea. They're all different kinds of qualities. This one obviously isn't going to solve. Unless I've got this set wrong. Nope, it's just all white. So that was a bad one to pick. There, that's a nice one. Here's a reasonably nice one. There are some weak ones. That's pretty good. So you got an idea what these images look like. I'm going to just throw them all in here and use this as a mass plate solver. And this is brave because these online demos are always interesting to do. All right, so just drag and drop. Bam, there they all are. Okay. And I'm going to tell it, don't write the WCS back out to the image because I don't want it to have, oh, WCS. I never said anything about it. World Coordinate System. That is the info in the FITS header that describes the plate solution. And the parameters for that tangent plane fit, and in the case of ACP, and also some other plate solvers have a different scheme, but either way, the optical distortion parameters are also written out there. So if you're using a similar solver later or go back and want to measure something in the image, you can do that. So WCS is where the plate solution is written. I'm not going to have Visual PinPoint write the WCS because I'm going to use this again to solve with all sky. And I don't want the WCS in there because it would be cheating. It would just, you know, already solved, right? So, and I'm going to turn off all sky. And then we're going to solve these plates. And you'll see this goes along pretty fast. Can you see this? Is this visible?
Yes.
Oh, good. Okay. So what's happening up here in the list of files is it's producing the star list. That's the detection, the list of stars that it detected. And that's used if you're doing asteroid hunting or other type of looking at the image again. You don't have to rescan the image. And for large images, it is a time saver. So it's just going along here. And so while we're solving all these images, I will go back and give you a little bit of info on the PinPoint, how the programming interface works. So instead of being a separate program, PinPoint's an engine. Astrometry.net, PlateSolve 3, and Astrotratia are all separate programs that you have to run either with a command line or something like that. And then they produce results, and whatever programs are using their results then will typically read an output file and extract the information that they're looking for and then use it. So it's a command line program with parameters going in and an image going in, and then the answers coming out into some kind of file or piped out. PinPoint, on the other hand, has a programming interface that is accessible from any of 20 languages on Windows. These are the infamous COM objects. This is not an ASCOM thing at all. This is just the basic language-independent object feature of the Windows OS. And so I'm showing you now one of the objects is the plate object, and that represents an image. And then once you attach the image to the engine, you have all of these parameters that you can look at. The histogram of the image, of the background mean and sigma, the actual image array, which you can then operate on with your own program. If you're doing different type of object detection, like inner aperture, that's for the aperture photometry detection. Centroiding method will be up here. CE. Centroid algorithm. Okay, so now you can pick whichever one of the type of algorithms that you want to use, and then the magic function call plate, that would be a method, plate.solve. That does the whole thing. What that will do then is produce a list of, well, the first thing it will do is it will fill in the right ascension and declination and position angle of the image, which once you do a plate.solve, you'll be able to get those. So let's say right ascension are there. That will be the very accurate RA as a result of the plate solution. So I'm not going to bore you all with programming stuff, but okay, we've done our thing. That was 140 images that got solved. They weren't overly big. Some of them did not get solved, as you can see. But most of them did. And for example, one of them, just to show you, let's see, can I make this bigger? This is Notepad++ tools. I should have done this before. I'm very sorry. Let's see, preferences. Can I change sorry guys, settings, preferences, editing. Well, I'm not going to waste too much more time. I'm looking for a way to make the font bigger, and I'm not. Can you see this okay?
I can see it. I think they could probably read it.
Sorry about this. I just think there must be a simple way to change general.
Maybe Control plus.
Let's try it. No. One more attempt here, and then I'm going to press on. I really am sorry I didn't have this ready for that. New documents, Roos's language, highlighting, print backup, multi-lens, weird. Editing, it should be there, but I don't see anything. God, there's got to be a way to change the font. View. Alt Control plus square. Really? Okay. Control scroll wheel. Hey,
there you go.
Alex, you win. You win it. Excellent. Okay, so thank you very much. Okay, Dave, I'm going to answer that question in a minute. The PinPoint is only telling you the center of the image. PinPoint doesn't slew anything. It doesn't do anything but tell you the center of the image. Let me get back to you. I see this here, and I will get back to you. So here's one of the plate solutions. What happened here is it found 45 image stars and 47 catalog stars, and solved using 27 of them. And this was the position angle and the full width half max, and this pointing error was 8 arc minutes for that. And I'm just going to go find another one that has a lot more stars in it. Here we go. 881 image stars and 1,073. I have it set for 500 max, as you can see. And again, it solved that in 4 seconds. So this kind of gives you an idea of what's going on here. Now, I'm going to cut this down to 1 just so we can do this, and I'll sky solve it, and let's see what happens with ANSVR or astrometry.net. And I really wanted to make this 15 minutes. All right, I'm going to end this with this one all sky solve, and you'll see ANSVR doing its thing here. Just a sec. Okay. And again, this is a 1-line call in PinPoint, but now off this thing goes. I know there's a way I can make the font bigger in this too, but properties. Let's make this font Lucida Console 18. Okay, that should be, there we go. Oh, that was pretty fast. All right, so let's look back. That was about 16 seconds for the first one, and it's solved in PinPoint in just like no time at all. That little one, the one I just put in there, but there it all is. And you can see this in ANSVR by doing that watch the log thing that he supplies with that. Okay, so. All right. Dave, how is Closeloop Slew on the Paramount similar or different from your PinPoint slew? PinPoint doesn't slew. It doesn't. All it does is solve for the center point. It's the closed-loop slewing is done by Maxim, Sequence Generator Pro, CCD Autopilot, CCD Commander, ACP. Those are the programs that accomplish the closed-loop slew. They do that by first aiming the telescope, then taking a picture, then solving the plate with whatever, the plate solver, taking the coordinates that came back from the plate solver, sending them back to the telescope and syncing, or in the case of the Paramount, which you can't sync into because you'll wreck the T-point model, instead it takes the actual correct coordinates and the desired coordinates, and it jogs the telescope, which then pulls your target into the center of the field by the amount of error that was measured by the difference between the actual and the where the telescope thinks it is. So it's all about how you get the, sorry, I'm sitting here being real animated and I'm still showing you this stuff. It's all about how the solved plate or the center point coordinates from the image, how they're used, and how the automation program uses the center point, the actual center point coordinates to correct. And that's, differs from the different things. Okay, we have Chris L. Hi, Bob. I understand the principle of plate solving. I'm more interested to know the use case of plate solving when taking photos. I know the solver can be used within other tools. Yes. Is why, and also when to use the plate solving in our workflow. For astro imaging, I don't know. I don't know what it is. For science, there's all kinds of things. A lot of you weren't here at the beginning of the program, and I will go back and tell you a use case of PinPoint not involved in pointing the telescope. And that was Dr. Donald Bruns took images of stars surrounding the sun. I am just amazed at myself for not having the picture of, I know I put that, well, shoot. All right. Nope. I'm really sorry about this, guys. This is what I do have, and that is okay. So I'll share my screen again. So the archive there, if you look up in the chat, there's articles, there's links to 3 articles, but here's one of Dr. Bruns's images processed to show you what he was trying to do.
We're not seeing your screen.
Oh, I got to push one more button here. How's that? There we go. Okay, sorry. So what happened is he went out and took images of at the 2017 solar eclipse, came back and then used PinPoint to measure hyper accurately the locations of the stars, the RN deck of those stars. And the result was his results measured star deflections were far more accurate than anything ever done by any professional or amateur. And it was within 0.05% of being exact of what the deflection should have been. So as it says, a good month for Einstein. This is the classical and quantum gravity article. It's probably the best one to read. It's very short. And then he has his archive. There's another article on IOP. All of these articles further up in the chat, I put the links. But that would be an example of using PinPoint to reduce data. Oh, another one. Back, I forget the name of the program, but they did an all-sky image that was then put into a planetarium. What was that? Hidden, I don't remember. It's been a long time, but they used PinPoint to flatten the distortion of the images that they took. They reversed out and then actually warped the images based on the distortion polynomial so they could stitch them together. That was another one. And you could do that. If you were interested in removing the optical distortion from an image after you took it, you could reverse it out. You would have to contact me and get the math needed, the 2-dimensional transform needed to undo the optical distortion in the actual image itself. I would do that, but for astroimaging, you're not ever going to notice that, and it would just be a waste of time, basically, for artistic. How much does binning impact plate solving in terms of lost accuracy? The plate solver should be able, for lost accuracy, I always think of the individual stars. For the center point of the image, it won't matter at all because, well, it'll be in the noise. You have 30 or 40 stars that have been measured, and they all have a little bit of positional noise. Let me get back, put myself back on the screen here. Okay, you have 30 or 40 stars. They all have a little bit of noise, but when you add them all in, take out the optical distortion, so it's 2 arc seconds of error in each one instead of 1. What are you looking for? Pointing your telescope again. It isn't going to matter at all. Whose telescopes need to point plus or minus an arc second? Nobody. So if what you're trying to do is just get a bad telescope to point better, any of these plate solvers will work. One thing I want to mention, and we're getting close on time, but there's one thing I really want to show you, and this should be an eye-opener. Typically, when doing astroimaging, you are taking pictures of big objects. This is a plot of the stars in the USNO A 2.0 catalog, and they're all like this. All the catalogs are like this, of M13. Here's the stars in the area of M13. Why is there a giant hole there? Because all of these star catalogs are produced by automated systems that go out and take images and try and measure the positions of stars. Well, you can't measure the position of a star inside a glob or in the middle of a galaxy or in a hot nebula. You just can't. So you end up with giant holes. So if you're taking a picture of a star cluster and then you go off and try and plate solve it, what's going to happen? If you have a low density catalog and a narrow field of view, so this is 13 by 17 arc minutes here. Let's see, 13 by 10. Imagine if you had a 10 by 12 arc minute field of view. You wouldn't have any stars in there for solution. So when you're taking pictures, astroimaging, oftentimes you'll have problem solving when you're pointed right at your desired object. I don't know about the other automation tools, but to get around that, what ACP will do, just as for reference, is it'll go, oh, yeah, probably this is not a good target. So it will step 2 fields of view towards the pole. That would be south in the southern hemisphere, north in the northern hemisphere. Take another pointing exposure and then measure it, and it'll almost always solve then. And then it still has the error because it just adds the 2 fields of view to the error and then centers the image. So it automatically will try again away from the image to get around this sort of problem. But once people see this should burn into your mind why you may have trouble plate solving pointed right square at a globular cluster or an other extended object.
Bob, did you say ACP does that?
Yes.
Yeah, okay.
PinPoint does nothing. I want to support that. I want to stress that. PinPoint does nothing. All it is a solving engine. PlateSolve 3 does nothing. All it does is solve and give you the center point coordinates. Astrometry.net does nothing. It only solves and figures out the RIN deck of the center of the image. What PinPoint also figures the RIN deck of everything else, but that's for what most of the people, if not every person on this show tonight, the main thing is getting your telescope to point, and that means any of the plate solvers will work, assuming you can get them to work. Let's see, we're at 7:27. Let me get one more, and then I want to explain what other things may, and I'm kind of going around and, randomly now, so I apologize for that. It's for building a pointing model. Okay. So build a pointing model. What you would do to build a pointing model is, once again, take a picture, look where the telescope's pointed. Take a picture. Well, no, look where the telescope thinks it's pointed. So you send the telescope to RIN deck here. Take a picture. Nope, you're pointed here. Well, now you have the wrong RIN deck and the right RIN deck for this place. Well, you plug that into your pointing model. That becomes a measurement. And you go to another place in the sky, click, and you compare and send that in. So each of those is a measurement of the pointing error at a different place in the sky. And as you feed the RIN deck, or actually it's the ALTAS, because that's what it's basically based on, is where the gravity vector, right? So, and then you feed that into the solver that figures out the pointing model. And after you feed it enough points, boom, it's got a pointing model, and that's how it gets there. So again, all the plate solver is doing is telling you the true center coordinates of an image. That's it.
I'm still looking at your screen.
Oh, okay. I'm sitting here. There. So thank you. All it does is it tells you the center point coordinates of an image. That's all these plate solvers do in any of these applications. What is the optimum exposure for plate solving? The longer the better, up to the point to where stars start clipping. The more signal to noise ratio you have, the more likely it is that the solver will detect the stars and will detect more stars. So here are and that's a really good question. And maybe it is at version 2, PlateSolve 2. Is that what it is? I thought it was PlateSolve 3 somehow. Anyway, whatever. It's the one from PlaneWave. So what are and I know we're at an hour. Can I get
You're fine as long as you're comfortable with it.
Oh, I'm fine. Yeah. As long as people aren't bailing out and
still viewers are growing. So
all right, good. Well, that's even better. So Uh, one of the problems with plate solving, the image itself. If you don't have enough stars in it, you're not going to be able to solve, right? And that's the question that was just asked. What's the optimum exposure? Well, the longer you go, the more stars are going to be detectable, right? So the longer is better up to a point. As soon as the stars start clipping, and you can afford to clip, a handful of them, big deal. But as soon as you start to clip the stars, now you're cutting the tops off the stars, and it's not going to be able to measure the centroid as well because you don't have a nice star profile. And if you're using a point spread function detector, which PinPoint by default does, now it's not going to fit that point spread function as well. And so you start running into trouble. The other thing that will get you in trouble on the image is streaking. If you can't track against the sky for 30 seconds or a minute to take a pointing exposure, and on a larger scopes, typically they're like 5 seconds, then you've got even bigger problems with your mount than just that it won't point, it won't even track. That's really bad. So, you need to do some work there. Mind you, I can speak from what ACP does to cut down on the amount of time it takes to do a pointing update. That is to take the picture and plate solve it. Somebody asked earlier about binning. Zach, what ACP does is it bends all the way up to 6 arc seconds per pixel if it can. And what that does, it has some benefits. As you bin up, it becomes more sensitive, right? You get more signal on the stars. You lose resolution and trade that for signal strength. So as you bin, you get more signal. Now you can shorten your pointing exposure. And who cares if the stars are each off by 3 or 4 arc seconds? Big deal. The center point coordinates are still going to be hyper accurate for your scope. So it does that. And so you get higher signal, better signal noise ratio, much faster download speed, and much faster scan speed in the plate solver because it's not having to cover so much area of image. So all of that adds up to the higher you bin, the better. Now, some of the plate solvers might not work well with high bin images. Well, okay. So the point is, expose as long as you can, bin as high as you can, get a good solid image that you can work with. That's, the better, the more stars, the better. Now for another issue. If you have a narrow field of view, you're using some catalogs, like typically the GuideStar catalog, which is a lightning fast catalog, and it has proper motions. So it's a really good catalog to use for solving. But it isn't good because it doesn't have very many stars in it. So if you have a narrow field of view, you could end up with only 10 or 20 stars in your field. That's not going to be enough. Really, what you want to have in your field is at least 20, 30 stars inside the field on average. If you can do that, you're going to be in good shape. And you need to have 20 or 30 stars in the image as well. So if you have a narrow field of view, you want to go to a more dense catalog, and I always recommend the A2.0. It doesn't have proper motions, so there's some little inaccuracies in there, but it's got a jillion stars. It's not too big, and it goes all the way down to mag 18. So if you really need, if you've got a narrow field of view, you may have to expose a little longer, get down to mag 16 or 17. You'll have plenty of stars to solve, and it'll work great. So there's that. And then the lastly, I should mention, if you see low numbers of stars in the solution where it says solved using 8 or 10 or 12 stars, believe it or not, there's a possibility that that's a false match. I never thought you could match 12 stars and still have it be false and be a high quality match, but I've seen it. So the additional check is on the plate scale. So you should put a plate scale in that's something like what you have and double check to see that scale that comes out of the solution is somewhere near your actual plate scale. A narrow field of view for the GuideStar catalog would be 10, 12 arc minutes on a side. That's pretty small. That's a long focal length and a tiny chip. Those days are kind of gone. The little little baby detectors on, you know, 3,000 millimeter scope, those days are pretty gone. So typically people's fields of view, even within 1 arc second per pixel, are more like 15, 18 arc minutes and or up. And if you're doing, you know, short focal length, you could have a half a degree field of view, which is now you're in great shape. No problem there at all. So those are the big issues. Not enough stars in the image, not enough stars in the catalog. Those are pretty much it. And if you're not doing all sky, having too big of a goof, you know, a mistake, and where you think that thing is pointed. By the way, all sky is slower, and period. I mean, it's just slower. If you're doing science, and this is where PinPoint really shines, is where you're cranking out images every few seconds, and it's solving in less than a second or a second. You can't get that kind of stuff from all sky. And yet, for the science, they need the WCS, the high accuracy WCS. So I have people doing, you know, time series of active things where they're taking an image every 10 seconds, and they need to have that solution done in a second or two. You have camera overhead and, you know, everything else downloading. And so they each have their place. And everything, I believe, is all sky, including PinPoint, as long as you have ANSVR, or if you want to wait the extra time to send it to astrometry.net by net. And if your scope points well enough, you don't need all sky at all, right? So really, if you're depending on all sky, then you've got a scope that points a field of view or more off on a regular basis. And that's generally the kind of the rule of thumb. If you can get your scope to point within a field of view, let's say you have a 15 arc minute field of view, if you can get it to point plus or minus 12 arc minutes or less, then you don't need all sky. But if you're out 30 arc minutes on a 12 arc minute field of view, it's hopeless. You're going to have to go all sky and take the extra time to solve all sky. So I think that pretty much wraps it up.
All right. Maybe if we have a few questions that we've been holding out from the guys in the room, we could always ask it. I'm actually a little curious. Are your
This is a good question.
No,
Ant-Man, way too much. Way too much. That I can't do that in 5 minutes or less. So sorry about that. Go ahead. I'm sorry. I interrupted you.
No problem. So I look at plate solving up until you're automated, maybe as a convenience. Once you're automated, it becomes necessary, right?
Yes.
You need to not have to worry about being pointed at the right spot. You need to be able to sleep through that, hopefully. So do you sell your product to people who are more remote or who are more casual observatory out in the backyard but automated? Or because I know PinPoint is basically considered, I'm going to say, the more bulletproof solution. And the people that I know of that are using it are remote in Arizona, New Mexico, not wanting to worry about it. I'm just curious.
We have about 1,000 people using ACP. Remote, only maybe a couple of hundred. So the vast majority are backyard observers, all automated. PinPoint came about in 2001 because I knew I would need something like that for the original ACP, which started in 1999 when it, you know, that's when I visited Kitt Peak and all of that. So the first thing I did before I ever started ACP was I spent about 6 months building PinPoint. So it was way before the other automated plate solvers out there. The only thing that was there at the time was Astrometrica, and that was one where you had to bring the image in and then click on the stars and then manually detect all the stars yourself and then push buttons and let it solve and keep solving and solving. And it had no distortion correction. So anyway, it specifically was designed and built to support automation. It is inside of Maxim DL, which has its own more or less manual and slightly automated observatory control, and it's there used for closed loop slewing as well. So Doug, way back when, Doug, George, and I did a technology swap where I have their pointing corrector inside ACP, which, by the way, is automated. It actually self-learns. As ACP runs, it continuously updates its pointing model. Every time it plate solves for any reason, it updates the pointing model. So that's inside ACP. And then for Maxim, there's the LE version of PinPoint, which has a lot of the more advanced astrometry functions disabled, but it will give you the center point coordinates, plate scale, and rotation angle, which you can use for rotator syncing and telescope syncing. So, but it's for automation, really, is what it's there for.
Now, I'll ask your opinion on this, because this becomes maybe it's a hot topic, I'll say, or one that might be a little bit cause some arguments. But plate solving or PinPoint in general, you can use PinPoint to generate a pointing model. Right?
Not by itself.
Not by itself, but you
the only thing PinPoint does is tell you where the telescope's pointed. So it has to be integrated some way. All pointing model generation programs use some kind of plate solver to tell them where the scope is really pointed when they send the scope to where they want it pointed. Mm-hmm. So PinPoint, yes, it's used. I think it's used in the astrophysics pointing, astrophysics command center. The pointing model generator there uses PinPoint as its solver. Right. For the sky, they have their own solver, and that is I should be ashamed of myself. There is a solver inside the sky as well, a plate solver. So, and I didn't say that, and I completely left it off the list, which I'm very sorry. To my apologies to Software Bisque, and it works quite well, and it's all sky also.
Mm-hmm. So now you can generate that pointing model. Take 100 or so. Well, I shouldn't say you can, but using whichever software you choose, whether it's APCC, the Sky, you can generate that pointing model, which I guess if you're in an observatory and you don't want to have to plate solve each individual image, you can rely on the pointing model. Or you can just plate solve and then reslew 20 to 30 seconds per target, not per image, per target, and then maybe on the meridian flip you do it one more time. So it becomes you can use it to do a very complex pointing model, or you can simply plate solve, reslew, and keep going. Right? You've got it. You can use it two different ways.
And actually, you probably want to use it both ways, because if you can rely on the pointing model to okay, so I can just say only can speak from ACP's point of view, it's usually less than 10 seconds for a pointing update. That is, take the picture, download, because it's high bend. It's 10 to 15 seconds. Now on a small scope, it might be 20 seconds or something. You're right. So, but anyway, that's what it is. But if you're astro imaging, now you're going to sit on that target for 2 hours. Who cares, right? Mm-hmm. So, but if you can avoid going all sky, you win, because those all sky solutions are slower. So if you can use your pointing model to get you close, and then use the pointing update to get you bang on, that's kind of the way to do it. Mm-hmm. The pointing model takes out the big errors, and then the final little error is removed by the pointing update. That is take a picture, solve it, and do that final tweak. So, but it's up to you. There are some scopes that are so good now, and these things are multiplying, 10 micron plane wave, and those that they all they need is a single sync at the beginning of the evening. So they start up, they home, and then they go observe. And this is within the case of ACP, they'll go observe, and the first target plate solution will cause a sync to be sent to the mount. After that, no more pointing updates. No, the only thing that gets solved is their final image if they want to. But you know, if they want the WCS in the image, but you don't need to mess with the telescope pointing anymore. It's now going to be 10, 15 arc seconds. So, because they're using encoders. So in that case, you don't even need that.
Yeah.
So the you know, the range of possibilities is all the way from slot car motors and nylon gears to synchros and encoders and, you know, whatever. But those mounts still need a pointing model because you have flexure. Just because the axes are very accurate doesn't mean the tube doesn't droop, and there's some non-orthogonal. If it's a German equatorial, there's non-orthogonal errors, and so you still have to model that stuff out.
Very cool. Well, one thing's for sure, plate solving makes all of our lives a lot easier. I remember back when I started out manually framing targets, and there were a few steps along my astrophotography journey where I was manually framing targets, get it in the center, okay, I'm good enough, right? Then when I started using Sequence Generator Pro, their framing wizard allowed me to look at an object and pick the region within it that I wanted to image, but that in and of itself required plate solving. I needed to make sure that it was pointing right on that small region, particularly with a long focal length scope. Even with a really good mount, I have an astrophysics, even with my really good mount, at long focal lengths, you're off by enough to make it not the framing you're choosing.
Well, and more importantly, with a long focal length, if you don't get it right on and you're guiding, you won't see your guide star, you know, with an off-axis guider. So I didn't mention that. It's part of the issues with automation, not with plate solving, because we were talking about is plate solving. But if you have an off-axis guider, you're going to probably have a rotator, and so the plate solver is going to have to give you your rotation angle too. And it's very important that the plate solver be rotation free. You should not have to tell it what your guess at your rotation is. So that's easy. And then that gives you your rotation back. And now you have the same sort of thing. You know what the mechanical rotation angle is, the angle that the rotator is giving you, and you know what the true sky position angle is, which is the key. When you're lining it up with a field of view indicator, like in Sequence or the sky, you have a field of view indicator with the guide chip on it, and you line that up and line it up like this. Now you have a 3-axis system, RA, deck, and position angle. You should be able to just feed that in, and then the system should take the scope, get it pointed right at your target, and get the rotator at that correct sky position angle. Boom, your guide star will be right there, and off you go.
Yep. One of the other conveniences it presents. I know Eric has talked about the difficulties of finding a guide star with a very long focal length scope. So
6,000 millimeters at New Mexico skies on the 24-inch f10 was what I cut my teeth on. So that, yeah, with a small guide chip.
Yeah.
247 guide chip. So that was interesting.
Okay. Well, yeah,
study.
thank you, Bob, for the presentation. It was a great presentation. Just excuse me, just a few weeks back, we were talking about how we wanted to have a conversation about plate solving, but basically all we could do was say, well, these buttons are here and this is what you do. So it's nice getting the background, what's actually going on from someone who knows what he's talking about. A lot of us just pretend.
Well, no, you're users. You don't need to know how it works inside, but I just thought it would be interesting for people to know all of the stuff that goes on behind the scenes. It's quite interesting.
Definitely was. Yeah, so thanks again. And guys, remember, you can always check these out on YouTube or on our website and past shows. I don't know what is next week yet. The following week, we have a newbie's journey in astrophotography. So that is something to look forward to. Next week,
Carrie from Farpoint is next week.
Oh, there you go. There you go. From Farpoint. I will get that scheduled sometime midweek so you guys can see it. And that's basically it for tonight. Bob, I do want to thank you again.
My pleasure.
Your website, pinpoint.com?
For PinPoint, it's pinpoint.dc3.com.
Oh, I wanted to ask you what DC3 meant.
Oh, yes. Let me answer your question the easy way. Just give me a moment. I
noticed that your company name is DC3 Dreams.
Right. Well, you probably, some people at least probably know that I'm a lifetime aviator. And so I'm going to try to find a picture for you that will give you the story the easy way. Just a moment. Okay, here it is. So I'll make this picture a bit bigger and share my screen again. Okay. This is a picture of me. I'm 2 years old. That's my mom. In the background is a DC-3. It's actually an old C-47 that belonged to my my granddad. My granddad, who had an aircraft overhaul shop in Southern California, and it was just, you know, the C-47. They made 20 or 30,000 of those things, and they were like everywhere after the war. And this is in 1947, eh? So 1948. I'm sorry, I'm 2 years old there, I think. And so that she used to close me in this crib. You'll see down here along the edge, that's a window, a screen door or window spring. You know what I mean? A screen door spring. And this whole thing was made out of just plain screen door screen. She closed the top and fasten it with a little hook, and then take the whole crib and put it in the airplane, and then we'd fly back and forth between Wyoming and California. And it was bumpy, and I'd just float around inside there, listening, hearing, smelling. It impressed me with that. And then, of course, when I got older, I wanted to ride in the jump seat. And then when I got older, I wanted to fly on the right seat. And so I grew up with aviation, and so I still have dreams of the DC-3. And so that's how I have the name for my company, DC-3 Dreams.
Very cool.
That's what I named it when I, whoops, did I unshare it? Yes, I did. Okay. Yeah. There you go.
Thank you. Thank you for sharing. Very cool. I don't think, I don't know. I don't think many of us have had an experience like that, getting around airplanes so young.
Pretty unique. All right.
All right. Well, they fully restored the Memphis Belle, right?
Yes.
I don't know if I used to love that movie as a child. Well, not as a child, as I don't know, younger. And I definitely want to see that, because it must be at the Smithsonian, I'm guessing. But
I think so. There is one right down here, a B-17 down here at Falcon Field, that is totally restored, and they fly, you know, you can get on it. You can just, you know, take a ride in it. It's pretty slick, and it flies right over my house. And the nice thing about the B-17 is that the engines on it are the R-1830s, which is 4 engines of what's on the DC-3. There's 2 of them, and that sound is just fabulous. That's all there is to it. Fabulous.
Great. Well, thanks again.
Okay. Well, thank you for having me on, and hopefully down the line sometime we can get back on and talk about ACP.
We'll try and do that. All right. Thanks again, Bob. Guys, thank you. We will see you all next week. Have a great week.